I'm going to do is Taylor's theorem, which we will get to by the end of today's class, and either finish it today, unlikely, or do it the next time. That is the multivariable Taylor's theorem, because I want to do the one variable Taylor's theorem also in class, even though you did it last semester. After that, we will really just do examples. I said earlier that the midterm week on Monday, if you had a class, we were going to do examples. So we will spend time looking at lots of examples until the next Friday. And it is only after that, after the second quiz, that we will get into new stuff. And that new stuff again will be just maxima and minima, which we will spend a little bit of time on. And only mid-April, we will get to some totally new considerations, which is inverse and implicit function theorem. So that's the plan. All right. So let's look at the statement that we proved last time. And I will just write the statement once again. So we saw, oh, okay, I have to share the screen. Okay. So we saw.
So could you also start the recording?
Yes, thank you.
Recording in progress.
All right, so what we saw is that the order of taking partial derivatives, whether with respect to one variable and then with respect to the second variable or the other way around, does not matter under favorable conditions. So let's write down what the conditions are. And so what we saw last time was the following. Suppose I just have a real valued function where U is an open set in R. So and the following such that d1 of f, which is just del by del x of f, d2 of f, which is del by del y of f. So this is just notation. And also this partial derivative, which is a double partial derivative. Okay, so I think we did it the other way last time, so not that it matters. And so that means what is the operation that is happening first to f, that is x, to derivative with respect to x. So let us suppose that all of these exist on U. That is, for every point in U, these operations are defined. That okay. And let us say then d21 of f at AB is equal to d12 of f at AB. Is this correct, what I have written?
D12 of x, we should prove that, right?
So what else is required?
So D21F has to be continuous.
Yes, and in fact, this is the whole crux of the matter, right? Without that, the result is not true. So this value, and so this is, and d21 of f. So remember, d21 of f is a function. Remember, we've said that this is a function that is defined on all of you. So it's continuous at a certain point a comma b. Then In fact, this is correct as stated, but we should. Then d12 of f exists and is equal. Okay. So now, last time there was some discussion about where this quantity, if I recall, we call this quantity delta of something, right? I don't recall the name. So where did that 4-term quantity, where did it come from? And I asked you to just sort of follow your nose and see what each one of these partial derivatives, if it exists, then what limit is, what is it? What is that quantity? So I have done this exercise, and I will write it down maybe in the next class, but I do want you to do it on your own. Okay. So what if d12 of f at a comma b exists, then what limit would it have to be? It would have to be a limit. It would have to be a double limit. Limit as h approaches 0 of limit as k approaches 0 of something or the other. And likewise for d21. So if you write down both of these things, then you will see that the quantity to which we applied the mean value theorem, you're forced to deal with that quantity. Anyway, but for now, we will just take this for granted. And so there is a simple corollary. So over here, we just assume continuity of one double partial derivative at a given point and said that the other way partial derivative also exists. But the following then is immediate. If f is in C2 of u, what does that mean?
The total derivative, like we can do that twice, and the total derivative is continuous.
The second total
derivative.
Derivative is continuous, right?
Yeah.
So in general, remember what Cn of u means. It means a function defined on u of which I can take the total derivative n times, and the result of doing the total derivative n times itself is a continuous function on u. But this just means now, so if the total derivative exists, then remember what we saw were the components of the total derivative. The components of any total derivative are just various partial derivatives of that order. So the second total derivative of f is going to have components that are, so in this case, how many components will it have? Remember, u is an open set in R2. So how many components will the second total derivative have?
4.
4 components, and we can in fact list them, right? They're going to be d11, d22, d12, and d21, which are respectively del by del x of f, and so on and so forth, right? But we also know that f being in C2 is really the same thing as all of these partial derivatives being continuous. So the hypotheses that are up there are, that is just easily satisfied. And what is the result? Then d12 of f equals d21 of f, not just at any given point, at each point. Just straightforward. Okay. So the point is, now I want to generalize this and have a version for. So here I had a single real valued function. F was just a real valued function on u, and it was a real valued function of 2 variables. But I want to take now any number of variables. Then the function target also is in some Rn. And I want to take partial derivatives, not just 2, but I want to take any number of partial derivatives. So in general, I have a situation like this. So several variables. and higher partial derivatives. So what is the situation? So let f be, so I have some open set now in not R2, but let's say some Rm, and f is a function from u to some Rn, our usual situation. And now I want to consider partial derivatives of kth order. And I want to have the analog of this corollary. So let's say I want to take the partial derivative first with respect to x3, then with respect to x7, then with respect to x1, let's say, right? So third partial derivative. And I want to say that these are that the operations can be interchanged. What should be the hypothesis on f? Okay, let me repeat this question just for definiteness. Let us suppose I want to say that I don't recall what I said, D417 of f at, it should be the same thing as D174. Okay. Suppose this is what I want. I'll erase this. Will this be true without any hypothesis on f? Well, certainly not, right? We saw that even in the two variable situation, I needed to have some hypothesis. So the hypothesis over there was that the function f needed to be C2. Will that be enough to make this assertion that I have?
So I think we need C3 here.
Right. So let's just see why we need C3, and the general case will follow, right? So I want to permute things, right? So notice that the given thing is not just an adjacent permutation. I have permuted. So if you wish, I have permuted, I have switched 1 and 4, and then I have switched again 4, sent 4 past 7, correct? So if I want to do this, so let us say I want to go via this, right? So first I want to say, so this is just rough work, all right? So this is, okay, so 4, 7 of it. And let us say at some fixed point. If this is the case, if I want to do this, then what is the minimal hypothesis that I need to have?
We need the the third partial derivative to exist, and also that f is in C2.
Right. So you see, if I first want to say that, if I just want to say that D17f is equal to D71 of f, just for that, it is enough to say that f is, f is C2 is certainly enough, right? For this. But then if I want to take the partial derivative with respect to the fourth variable, then I need that partial derivative to exist. And certainly if f has the third derivative, then in particular, this component partial derivative will exist, right? But now, suppose I want to also switch the 4 with 7. Then you see, I will need the continuity of the requisite partial derivative also here, the requisite double partial derivative. So what is the simplest way to achieve this? I was just trying to motivate what the hypothesis is going to be.
So we could try and enforce like C2 on the, like, I don't know if it won't be C2, but if we just try and have continuity of like C2 on the first two variables from the left. I
Right.
think that way we can permute the first two variables, and then we can permute the next two.
Right. But you see, if I want to take third partial derivative, if I want equality of third partial derivatives, then wherever you have done this permutation, then I need to be able to take partial derivatives of that, correct?
Yeah.
And notice, there is yet another thing. Let us say I want to do something like this, okay? So let's say D73459 equals D73549, correct? Then notice that this continuity of the second partial derivative, I need that not for f, but for the partial derivative of f with respect to the ninth variable. Do you see this? because I'm switching 4, 5 and 5, 4. In order to use my earlier result, the function to which I'm applying this is not f. The function to which I'm applying the switching result that I have earlier is the partial derivative of f with respect to the ninth variable. Yes? That function needs to be C2 with respect to the fourth and fifth variable. And doing that then needs to have partial derivatives with respect to the seventh and third variable. Right? So you see it gets awkward.
Yes.
Right? Whereas the hypothesis is simply a CK map, i.e. The kth total derivative f sub k is defined or not is defined, is exists. And is continuous on all of you. Okay. So then what is the statement? Then I'm going to take kth partial derivatives. So I1, I2 up to Ik of f at any point in U is equal to what?
Any permutation of these I1 to Ik.
Right, any permutations of these I1 through Ik. So the way to do this is di sigma 1 to I sigma k of f. This is a bit formal, but what we really are saying is that the subscripts of the i's are permuted, right? See, for all I know, all the i's may be 3. In which case I can permute, nothing happens. And the theorem is this statement is content free in that case, but that is also true. So we can just say, for example, and whatever, so something B2 4714 F is equal to D whatever 42471. All right, so this should be intuitively clear, but how do I actually prove this?
Sir, any permutation is just a product of, is like a composition of transpositions.
Correct.
And so
I should be able to switch any 2 at a time.
Yeah.
And that will give me everything. Okay.
Yeah.
But how do I switch any 2 at a time?
We have, since its map is CK, which means that all the partial derivatives of all the functions exist, or of all the, or like the partial derivatives of all the partial derivatives exist, and we can switch them because they're all continuous.
Right. Okay. So that is still slightly cavalier, but let's say more about this. So this is a CK function. So just the characterization of C1 functions, just bootstrapped, tells me that that is equivalent to saying that all of these partial derivatives, di1, I2 up to Ik of f exist. That is what is going to give me the matrix of this total kth derivative. And not only that, they are all continuous. That is really equivalent to saying CK. So all of these are continuous. All right. So let us say I want to switch I1 and I2. What do I do? I apply the above result to which functions?
To like the k minus 2 partial derivatives of f.
Right. Okay. So before that, I should say one thing. F really has many components, right? Because the target is in Rn. But this is neither here nor there. Because I know that a function that has a function that is that takes values in Rn, I can think of this as a vector valued function, and I can deal with it component wise. Yeah. So whatever I have written over here, d of whatever of f, it really is a vector valued function. So I can, so this equality is really equality of those partial derivatives applied to each component f sub j, where j goes from 1 to n, right? So I'm back in the real valued situation. And then for that real valued situation, if I want to switch any two slots, let us say k is equal to 10, and I want to switch slots number 5 and 6. Then what I have to do is I first have to apply the partial derivative, the degree 4 partial derivative of indices in slot number 7, 8, 9, 10. Okay. As a result, I will get a function that still is sorry. So what is that? The result of doing that is still going to be differentiable. In fact, it will have partial derivatives, continuous partial derivatives of order 6. But in particular, it's a C2 function, right? So I can switch the next two slots. And then all I have to do is whatever are the first 4 things, I just have to apply to it. Okay. So I hope this is clear. So proof, let me just mix.
I'm sorry, I just want to clarify something. Does this in effect mean that we're taking ck to mean that, let's say, all the ith, like the components of, let's say, the ith derivatives are all ck minus I, for all I from
just think about this. Okay, so let's just remark on this. Okay, so remark. Okay, you know what? So let's so let me take a special case. Suppose some function is C7, right? C7. Suppose I take a second partial derivative of this function with respect to some variables. Is this C5? Just check.
It should be, right, sir, because we.
What does it mean for a function to be C7? Partial derivatives exist, but that just means that if I take all possible degree 2 partial derivatives, then I can take all degree 5 partial derivatives of those derivatives, and they will be continuous. No, I mean, it's just, there is nothing to this. It's just rewording. So yes, what you're saying is absolutely right, but it's also easy. So proof, I'll just take some, maybe, so may take. So what would I have? M equal to 1. With component real valued functions. Let me not be lazy. So this is just sort of an initial comment. Then for k greater than, for k equal to 2, we have already proved the result. Keep all but and use earlier result. Earlier result. So this could be for requisite partial derivative of, not just for f, I have to use this for partial derivatives of f, and also I should really say in between that any permutation can be obtained using, that's the remark, any permutation can be realized as a sequence of transpositions. Okay, good. So any questions so far? Very well. So there is one more sort of remark to say, and this is just really a counting remark. Okay, so this is just an example, right? So let's just see an example. So question is, how many so this is for a CK function, right? So in the so if CK, then how many different sequences of partial derivatives operations, partial of kth partial derivative no, that sentence is getting out of control here. How many different sequence of k partial derivatives, partial of k partial derivatives it's harder to formulate than actually to state the result, especially in an example. How many different sequences of k partial derivatives are equal by the above result? So just for example, if I am taking D413 is equal to how many? So for example, this is D also 143, right? So in all, how many such things are there? This has nothing to do with analysis. This is counting. So how many possibilities are there? Come on, this is straightforward. All I'm asking
3
is
factorial.
Yeah. So this is so six equal terms, 6 equal quantities. So in general, such a thing, I1 up to Ik, will it always be k factorial different equalities, k factorial different quantities being equal?
No, sir. Like we can have.
No, because some of the i's could repeat, right? So this is a simple counting. But for example, if I have D41431 is equal to how many quantities? And we can calculate this, right? So this is straightforward counting. This is 6 factorial divided by
3 factorial into 2 factorial.
sorry, yeah, 3 factorial times 2 factorial times 1 factorial. It's a multinomial coefficient, right? But here's one more thing. Each equal to, I can sort of write down what this is, no? Because I can write this in some kind of standard order. So I can say that this is really the same thing as D1, this operation applied 3 times. Then D3 applied once and D4 applied twice, correct? Which is really, if you want to write, it is 1, 1, 1, 3, 4, 4. This is a purely combinatorial point that is being made. And the only reason why this point is made is because when we write down Taylor's theorem, Taylor's theorem will involve taking higher order derivatives, but we are in a multivariable situation. So that means that all possible partial derivatives up to the desired degree of accuracy will have to be involved. But because of this symmetry, what will happen is that even though each one of the terms will come, a certain terms will repeat. And so we might as well combine them into a single term. And so this is the count about what coefficient we are going to get. All right, that's all that is happening over here.
Sir, so if the function is C4, if the function is C2 and we are taking four partial derivatives, and if the first two indices are equal, then can't we permute the last two indices if they all exist?
Okay, all right. So let me see if I understand the question. So you are given a C2 function, and then what do you want to do? Just for example, let's say of whatever number of variables. What do you want to do now?
I want to take four partial derivatives. They all exist.
Okay, so but that now has to be an extra hypothesis, right?
Yeah.
Because your hypothesis guarantees only that double partial derivatives exist and they are all continuous. That's all that it guarantees. Okay, so then okay, so let me see if I understand what you're saying is right. So just a sort of remark. So let us say this is an aside. F is C2 and D, let us say something whatever 2, 3, 1, 4 exists. Then you want to say that D2314 of F is also equal to D of what?
2341.
2341. Okay, just think about this. Do you agree? Does everyone see this, or is there any objection? Okay, so let us see why this is the case. So first of all, I simply throw away those 2 and 3, right? I simply look at D14 of F and D41 of F. Yes? Now let's look at the proof. So in fact, this is good. So this business of keeping all but 2 variables fixed. So let's just do that, right? So what I'm doing is, let us say there are only 4 variables. So I keep x2 and x3 fixed. So let us say I want to show the equality of these 2 derivatives at any given point. Right? So this will have 4 components. The second component and the third component I will just hold fixed and look at only variation of only with respect to not component of the variable, only the first and 4 variables. Then this becomes a function of function on R2, some open set in R2. Right? I have intersected the given open set with R2 to get an open set in R2. And now the old proof just applies directly, and I will get D14 of F at the given point is equal to D41 of F at the given point. Now you just tack on 2 and 3 because you told me by hypothesis that this derivative existed, this partial derivative D23 of D14 of F existed, but D14 of F is equal to D41 of F. So this is all straightforward. Right?
Okay, sir.
Yeah. So let me just say because D14 of F no, I should say it the other way around. Psychologically, because D14 is given to me. So sorry. Because D41F exists and is equal to D14 by the above result. And D is just D23 of D41. That's all. Which exists because D41 of F is etc. Okay. So all right. So anything else? Okay, so let's move to Taylor's theorem. So All right. I asked you to read the one variable proof, but we will still go through it because it is nice and instructive. And especially since I made a mistake once with the mean value theorem, I have to atone for it repeatedly. But let's first write down the multivariable theorem. Okay. So statement. And then we will work towards it. So suppose I have the following situation. Suppose I have an open set in, or okay, so usually I'm taking the source to be Rm and target to be Rn. But here, let me just take Rn. I'm just going to be following Pramad's notes. So here, let me just stick with this notation. And I just have a real valued function, f, which is a real valued function from U to R. So you see, the idea is going to be to try to approximate f near a point using values of f as well as the values of derivative of f at that point, correct? It's a real valued function, so I can just talk about approximation just in terms of how much the difference between the real numbers is. Okay, so a CM map for some m greater than and suppose I have this point A, which is a reference point which is given. So I'm going to approximate f in some neighborhood of this point. So given some point A in W, let me first write down. So what is the kind of thing that we want to write? F of A plus H is equal to something, right? So what is the one variable version? The one variable version, let's write down the one variable version. And then you should tell me what the so this is going to be, so this is just for reference. F of A equals, F of so in one variable. F of A plus H is what? F of A plus 1. So this should be easy. Come on.
H of dash of
F prime of A times
x by 1 factorial.
Right. So F prime of, so you see, I have already said it A plus H rather than X. So instead of X minus A, I simply say F prime of A times, come on, it's times H, no? Plus F double prime of A by 2 factorial times H square, etc. And how long does this go? Where does this end? There should be no hesitation about.
This ends at differentiating f prime f m minus 1 times, and then we have the remainder term which
Exactly.
is
So
differentiating m times.
So the same pattern goes until n minus 1 factorial and h to the n minus 1. Now there is this remainder term. What about the remainder term? So there is h to the n and there is the divided by n factorial. But what is the form of the remainder term?
It is f differentiated n times of c for some c in A to A plus h.
For c strictly between A and A plus h. I don't want to write the interval from A to A plus h because h could be negative, right? So C for some C strictly between these. Okay, so this is the one variable version. What do you think it should be in? What should happen in multiple variables? There should be a similar format. What is the difficulty?
is a vector.
Yeah, sorry, say that again.
H is a vector.
H is a vector. So H will have multiple components, right? So H will be some vector which is, let's say, H1 up to, so U is in Rn, so H is going to have H1 up to Hn. So what will powers of H mean? And a related question, what does it mean to take the derivative of F? All those derivative terms, they will be matrices, you see. I want a real number finally. So what do I do?
Bring everything to one side and take a norm.
Okay. So, but you see, really the values of all partial derivatives are going to be required, because if you want to step in the x1 direction, then you actually see the norm of this matrix is a single number that sort of takes into account all directions and then just gives a single number out of it. Whereas here you really do need to keep track of what is happening in each direction separately. So we cannot use just the norm of the matrix. Rather, we will need to use all the partial derivatives, each one of them. So instead of f prime, what I need to have over there is that all the partial derivatives in each one of the n directions. And then what should happen? So let's just look at the first step, all right? So, so this is all sort of still rougher. So how to change this? How to change this? In multivariable, in many variables, or for many variables. So f of a will stay f of a, but what will happen? That f prime of a times h, how will that term change?
That will just be the gradient of f times like the vector that represents.
Exactly. So very good. Now we can say gradient times the vector, but gradient is a vector, h is also a vector. So what do you mean times the vector?
So the scalar product.
Right. Right. Okay. So you want to think of this as a gradient as a vector, but really just think of f prime as a matrix. No? What are the dimensions of this matrix?
Oh, sorry, right. We're not just looking at a single component of.
Right. Okay.
Sorry.
So there is a way to think of this. So h, if I think of h as a column vector, then what is f prime of a as a matrix? What are its dimensions? Remember, the original map is from n dimensions to 1 dimension. So the derivative of this is going to be a row vector, right? So here actually we are still okay. Here we are still okay because I can meaningfully think of this as, so here this just becomes whatever d1f of a up to dnf of a. If I write this as a column, then this will be the gradient vector times h1 up to hn. That is still going to give me, so this is what the second term becomes. Is this okay?
Yes, sir.
All right. But then what happens? What happens with the third term? So here, this one, what happens? Now I have h square, you see.
So what you can do for, would this work as in you take the row vector representing h, right? Because the second derivative would be would be a matrix, right? It won't just be a row vector anymore. So you have
Right.
the row vector representing h multiplied on the left of the matrix, the column vector multiplied to the right of the matrix, and then you get a scalar.
Okay, so you want to still somehow play with h, right? H being, so you still want to play with, okay, I understand. So as I understand, what you want to do is you want to take this matrix and you want to put h on one side and h transpose on the other side somehow to get a scalar, right?
Yes, yes.
Okay, so let's examine this a little bit. Okay, so I didn't think of it.
But the last entry should be DNFC, right?
Sorry, 1 second. No, sorry. So you're saying something else, or
Sir, in the row, I mean D1FA, D2FA, up to DNF of F evaluated at FC, right?
are you talking about the
X.
linear term, the one that I have finished? Are you
Yes,
talking
sir.
about this?
Yes, sir.
But no, you see, I mean, the number C, the error term, that will come only at the nth degree term. So here there is no issue. Oh, okay. I'm very sorry. I'm very sorry. Okay. So you tell me what mistake I made. My bad. You see, this is a CM map. So I got my M's and N's mixed. So you see, in the Taylor approximation, I'm going only up to mth stage, not nth stage. I should not mix up those two. Okay. You see, I have taken this to be something that can be differentiated m times, right? So this is m. Okay. I hope that clarifies. The m and the n, they are completely different. You see, the degree of accuracy that I have depends on how many times I'm able to differentiate continuously. That and the number of variables have nothing to do with each other. Okay. So, okay. So coming to the second order term, but you see, what if you go to the next one, the degree 3 term? Then whatever you are trying, that doesn't really generalize, no? If I have h taken 3 times.
Right. Yeah, we don't have like actually what would that object even be like? Because if the derivative, right, it's not something we can actually like really write down or manipulate in any
No, but what do you
intuitive
mean?
way, right?
No, but you see that whichever derivative you are taking, we know it as a matrix. It will have many components, but it is just the matrix consisting of all the partial derivatives. Maybe I should not say matrix. It's a multi-dimensional array consisting of all possible partial derivatives.
Yes, sir, I meant that. Like, I mean,
Right.
like we like this thing of taking H transpose times the second derivative matrix
But
times
okay,
H
but
was
let's just look at the degree 2 term. Okay, so let us suppose I'm looking at the component which is d35, right? That is partial derivative in the third and the fifth direction applied consecutively. Now you see the degree of approximation that I mean the error term that I need to add thanks to this derivative. This should depend only. So you see, I'm going in only in the third and the fifth direction, right? So what the amount that this should contribute to correcting my guess, what this should go with, it should this term go with all components of H? Will all components of H matter? So there is H1, H2, H3, H4, H5, whatever. And now I'm taking the D35 derivative.
No, only the H3 and H5 things should
Right.
matter.
And
So
in fact, how should they? The first term that should tell you exactly what to do. So in the first term, what am I doing? I'm multiplying D1 with H1. I'm multiplying the value of D2 with H2, and I'm adding them, right? So that is giving me the approximation. So this is telling you what should happen in the next term, no?
yeah, I guess we could. So for 3-5, we would multiply by
Multiply it
H3,
with, right. So in fact, let us see. So this is terms like. So I'm just going to say terms like Dij of f at A times Hij, correct? And of course, that should be divided by So summation of terms like that divided by, now, okay, divided by 2 factorial times what? Okay, I already wrote HIHG and so on. It is going to go in this fashion, correct? But notice one thing, there is some kind of counting thing here, right? So let's try to guess this formula. So this is going to be one summation k equal to 0 to m minus 1. The remainder term I'm going to write separately because that is evaluated at some other point. So what will be the general form?
So if we keep applying H and then transposing.
Right. So, okay, let us see. So you see, in the kth term, I'm taking k partial derivatives. So that means that the d1, so it is going to be really things of the type di1 times di1, di1, I2 up to ik. But my count tells me that when I take di1 up to ik, it is better to group it by how many times 1 comes, how many times 2 comes, and so on and so forth, right? So let us group it like that. So if I take d1 coming s1 times up to okay, how many variables do I have? N, Sn times. And if I take that partial derivative applied to A, every such term I have to divide by how many factorial? K factorial, right? Remember, this is the degree K term. So such that S1 plus S2 up to Sn equal to K. You see, kth partial derivative is being taken. Now the thing is how many times, so this I have to really divide by K factorial, right? Every time such a term comes, but how many such terms are coming? Just look up here. It is going to come K factorial divided by S1 factorial up to Sn factorial. So the K factorial cancels and I simply get this term divided by epsilon. Okay, so this is exactly like saying, okay, so let me just say, so this is exactly like saying, see this D414311, that term, of course, applied to F and evaluated at A. When that comes, that will be divided by 6 factorial, right? In the Taylor series Taylor expansion, because it is the 6th derivative that I'm taking. So you see, but when I'm dividing it by 6 factorial, the number of terms that are coming of that type are 6 factorial divided by 3 factorial times 2 factorial times 1 factorial. No? So when I just gather all of these terms together, the divided by 6 factorial will cancel with this 6 factorial, and I will simply get this term left in the denominator. That's what I have. Okay. But what will this get multiplied by? Look below. Dij of F evaluated at A, that gets multiplied by, for each, yeah, correct. So tell me.
So it should be h1 to the power of s1 all the way
exactly.
to
So the number of times I'm applying d1, then h1 will contribute to the correction in that direction, right? So this is simply gets multiplied by h1 to the s1, h2 to the s2, all the way up to okay, so hn to the sn. Okay. Of course, this is wrong, because what we have is the analog of, so I'm just going to put this as a rough work over here, right? So this is just rough work. So heuristic. What is left?
The remainder term.
Plus the remainder term, correct? So plus, so remainder term, let's just say R of H.
So, sir, the original form of the remainder term, at least in the one variable case, is the integral, right, over the integral which we simplified with the mean value theorem. So,
Yes.
Now for this one,
yes.
will it also be like an n-fold integral of
Yes.
sorts? Or?
What we are going to do in the proof is that it really is going to be just a straight application of mean value theorem. So let me just write it down, and then maybe we can discuss it afterwards. So remainder term RH. You know what? Remainder term where, and then this continues. So where RH is of the form and we can really just write this. See, the remainder term is really of the same type, right? It is just that instead of evaluating it at A, I'm evaluating it at some point, right? So it's going to be exactly a term of this kind. Except now the value of K will be what will be the value of K?
M.
M, exactly, that's all. Where this is of the type summation S1 plus S2 plus up to Sn equals M of the exact same thing, D1 to the S1 up to N to the Sn of F, but applied to something else and divided by S1 factorial times up to Sn factorial times H1 to the S1 up to Hn to the Sn. All that stays the same. Now, instead of evaluating it at A, I'm going to be evaluating it at, where do you think I'm going to be evaluating it at? So the 2 points that I'm considering are A, that's where my, that's my reference point. And the point at which I'm trying to approximate is A plus H. So where do you think this in between this point should be? And this will also give you a clue about how the proof is going to go.
Something like lambda A plus 1 minus lambda H, or
right.
somewhere in the middle.
Okay. So, but yeah, okay. But it's basically just going to be in the segment joining them. So we are going to call this A plus theta H, and that theta is like the C, where theta is what? Is just a real number between this is just a parameterized line segment joining A and A plus H. So theta is going to be taking values between 0 and 1, right? So theta is just something strictly between 0 and 1. Okay. So in particular, okay, so we can say next time what the so note that RH by H as H goes to 0, what is the order of, how good is this approximation? If I divide it by H to the M, then it's not so good because I'm just going to get a number. Also, what do I mean by dividing by H? Of course, norm. But if I divide by the norm of H to the M minus 1, then you see some H terms will still be left. So this is 0. So this is telling you how good the approximation is. Right? So let me just finish stating the theorem. Multivariable Taylor theorem. I did not state the hypothesis completely. So U is an open set and I'm taking a point in between. I'm given A. So now this a plus h I just introduced. Can h be arbitrary?
No, it has to lie within U.
Right, but you see, it has to lie in U, but can it be anything in U? Imagine that if the set is not convex or something like that. I see the proof of this theorem is going to be just a straight application of one variable Taylor's theorem. What am I going to do? I'm going to
segment
take,
joining
yeah,
A
so
and H should lie in U.
correct. So now you see the line segment joining A and A plus H. What is that? I can think of this as a map from 0, 1, the closed interval 0, 1, landing into U, correct? I will simply take the composition of this function from R to U with the given function f from U to R. And I'm going to get an ordinary function of one real variable, and I will just apply the Taylor theorem to that. Okay. And of course, what is going to happen is that I'm going to apply this Taylor's theorem to a composite of two functions, which gives me a single function, which gives me a function of a single variable. So I have to take the derivatives of this function, which is a composite. So what do I have to use to unwind all of this? I'm taking the derivative of a composite function. So what do I have to do? Use the chain rule. And then this entire thing will simply write itself out. Okay. But the point is that, so yes, you're right, that this entire segment must be in U. So I can say that U is convex, but I can simply say instead that, see, I want it to be true for every point in U, right? So instead, what I will do is that instead of having any hypothesis about U, what we will say is that around any point I can put a convex thing, no? I can put a ball. So that's what I will do. So, given for any H in some neighborhood of 0, okay, so let me even name this neighborhood following some neighborhood W of 0. We have W plus mu, and so I hope you can parse this. What we are simply saying is that just put a little ball around U, a little ball in U around A, so that it is entirely contained in U. And I can think of this as a translate of a ball near 0 just by adding A. The reason why I'm doing it this way is I'm thinking of H as something small. H is added to A, no? So H is something small. So H is in some small neighborhood of 0. Okay. So proof idea. Use one variable Taylor theorem for the composite function zero, 1 to U. This is f. And what is the function over here? Yeah, so what is the function? Come on, this is straightforward now. All right, so let's make a variable t. Where does t go?
TA plus 1 minus TH.
But it's already between 0 and 1, you see. So, okay, at 0, what should be the value?
A.
A. So you just say A plus, and at 1, the value should be A plus H. So A plus TH. So G of T is equal to F of A plus TH. To calculate G prime, to calculate derivatives of G. There will be many derivatives, right? To calculate and that's really the proof. Okay, so we are just about out of time, maybe a minute or two at most. Are there any questions?
Sir?
Yes.
Yeah, I have a question. Why should A be, why should it be convex? I know here we're using like the straight line, right? As in,
Right.
but how do we know it's necessary for you to be convex?
No, you absolutely need not be convex. So let's actually go and look at the statement carefully, right? So in fact, let me draw a picture. So you see, U is an open set. Given a point in U, we are saying in some neighborhood of 0. So let's draw a picture. I'm allowed to choose that neighborhood. So here is the thing. Let us suppose U may be some set like this, whatever, correct? And A may be over here. So this is U. Let me not put A that close, So let us say A is over here. So of course, I'm not going to choose A plus H over here. No. But what I will do is that I will put a ball around here. And I'm going to make the statement only for things in this ball. Right?
Yes.
So is that clear? The choice of W is up to me.
So we need convexity only because like it becomes simpler in the proof to use a line between A and B. Is that correct?
You could use some other curve. Yes, you could use some other curve. But you see, then calculating what does it mean to use the chain rule? That means I have to calculate the derivative of each function. No? Now, what is the derivative of the first function? A plus TH. Right? Yeah, so I mean that's a linear function. So you can actually make the calculation. I mean, there is nothing wrong in taking a composite for some other curve, and we do this. At times we certainly do this. You can put some curve and then compose and then take the derivative. But here, this is what allows us to do the calculation and get the form.
Yes, sir.
Right.
Oh, and sir, I have another question. I mean, this is I know we've done a lot of differentiation, but I still don't understand why like the derivative has to necessarily be a linear map. I mean, assuming it's a linear map, we get nice properties. But why should it be a linear map to begin with? I don't know.
I mean, so the safe and sort of easily answer is that we defined it to be a linear.
Okay.
But you see, we want it to be a linear map because you should think of the derivative as a. By the way, we should really stop now. So feel free to go. Now we are just going to have a discussion. You see, even in one variable situation, the derivative is not a number; it's that line.
Yeah.
Which is a linear gadget.
So it's just convenience, is that correct? Like we want.
But you see, the whole idea of the derivative is that you want to analyze the function that infinitesimally you want to approximate it with a line.
Yeah.
So right. So we want the derivative to be a linear function.
Yes.
In analogy with one variable. All right. So the next time what we are going to do is, by the way, so essentially what we have done is we have done the proof, of this theorem. Now it is your job to just see how to apply this, to calculate this this derivative. Because we wrote down the one variable Taylor's theorem, and I told you now by taking this composite of a line with the given function, we are reduced to that situation. So now it's just a matter of writing down the chain rule and seeing what expression you get. Okay, so this is something that you really must do on your own. We will do it next time, but it's much more illuminating if you do things on your own. And also read the proof of one variable Taylor's theorem. It is a very nice proof. I will quickly sketch that also. Okay, so let's stop for this time.
Sir?
Yeah, so just give me a moment, please.
Sure.
Okay, because we will let whoever wants to leave, people can leave. I'll also stop recording and then we'll continue discussion.
Recording stopped.
Yes, go ahead, please.
Yes, sir. I don't know if this is like a reasonable question or like a demand, but the thing is, like, I've always thought of Taylor's theorem in the one variable case at least as like the best way we can approximate like a function around like a point. So like we compare the values. So if I take small enough h, then so can you just scroll up to the one variable case?
Sorry, to the one variable version.
Yes. Yeah. So here, if I take small enough h, then all the higher order derivatives will cancel out, and I'm just looking at my claim, like the way I'm picturing it is that if I take small enough h, then the values must be same. If I take, I don't know, slightly larger h's so that I can only ignore the h square and above terms, then I need the derivatives to be the same. So like if I bring over f of a to the other side, then I divide by h, then it has to tend to the derivative, and I keep doing this. So like that's the strategy I'm using to approximate at a plus h. Like, is there an analog of that in the multivariable case? So I was just trying to get a good picture in my head. That's all.
Okay, so how would you imitate this procedure?
I'm not really sure, so that's why I asked. But like
but you see, okay, so see, part of it I can certainly get started with. So of course you have to do the approximation where f of a plus h is roughly equal to f of a to the zero, right? Okay, so now but how much do I need to add? So you see, linearly it is not difficult to see, because what you are doing, so that f prime of a times h, it really is correct. As it stands, it is correct in the multivariable case. Of course, multivariable means for a single real number of function of many variables. And then it is okay, no? Because what you are seeing is you are seeing the slope in each one of the directions, each one of the independent directions, principal directions. And you are seeing how much you are stepping in each one of the directions, how much h is varying, right? So that part is okay. Now, how would you go from that?
That's exactly
how do you go further? No, but then this brings me back to the question: how are you doing this even in one variable case? What is your idea?
Right.
So I have f. So now I'm considering f of a plus h minus f of a minus f prime of a times h.
Right. Now I divide h on both sides, so I get f of a plus h minus f of a by h minus f dash a whole divided by h. So
okay.
Yeah.
But right. Okay. But what about this? So what about this now?
Really.
And if you go further, you see, the thing is, how are you going to explain the factorials?
Yeah, that's also there. Right. Okay, maybe I need to reinterpret.
Okay, so but maybe let me suggest something. So the way I think of it, again, I'm not an analyst, so this may be. I mean, I think what I'm saying is not wrong, but it may still be too cool. The point is, what are the nice? So I want to approximate the given function using a nice function. What are the nicest functions? Well, there are constant functions. That's what f of x equals f of a. That's what it would do. But really, the nicest functions maybe are linear functions, right? So the linear approximation f of a plus f prime of a times h is good. I mean, that's what you first do. No, that's the first level in calculus, which is you approximate the graph with the tangent line. Infinitesimally, that is good. But now here comes the sort of next little thing. What are the next, so if I go in this hierarchy, then what is the next natural candidate? I have a constant function, then the linear function. So nice functions are polynomial functions.
Yes.
So what is the best quadratic what is the best quadratic polynomial to approximate the given function? And then this 2 factorial or the higher factorials, that comes with the idea of matching. I'm matching some aspects of the given function. First, I match its value. Then I match its derivative. Of course, all of it at the reference point. Okay. Then I match the second derivative. And these 2 things together tell me that the coefficient of the quadratic term has to be the double derivative divided by 2 factorial. Right? And then you go on. So basically, I am trying to approximate the given function with a polynomial function.
Yep.
And then the nice thing over here is that when I do this, somehow the error term can also be thought of as a power of the next degree. And the only thing is that the value at which you, sorry, this is, I should write this as f m. The value at which you evaluate this next derivative is just some in between point. Anyway, I mean, that's sort of my way of thinking of it. It's I don't know that. So I think this is okay as far as it goes. I don't know if there is any deeper way of understanding.
Yes. Like, how does that translate into the
okay. So now, if you want to do this, okay. So then we can okay, but I think then this may also be all right, because now we say I have a okay. So let's look at this. You see, this function now in the multivariable situation, it is still a polynomial function.
Yeah.
Of h as a vector, right? It's a polynomial in many variables, the variables hi's, right? And I think what is going to happen now is that if I calculate all partial derivatives up to the m-1 order, they will match.
Yeah, right. Okay. That actually makes sense.
Right. And okay. Yeah, and so okay, so maybe I should have said this in class that this is one way. So so on Monday I will yeah, so next week the plan is the following. There is really nothing new. So we will finish off this Taylor's theorem. I mean, you stated it, but we will write the proof. And again, if you do the one variable Taylor's theorem, that is really where the nice thing lies. The multivariable Taylor's theorem is, we sketch the proof. It's just carrying out this chain rule, and it just falls in your lap. I want to revisit the proof for the mixed partial derivatives in light of the question that was asked last time. So what I want you to do is just write down what D12 of f is. Just follow your notes and write what D21 is. Do D12f, D12 of f, and D21 of f. And you will see that your effect you can formulate it in such a way that you are effectively calculating the derivative, the limit of the same quantity divided by h times k, but in the opposite order. Once as h goes to 0, and then as k goes to 0, and then the other way around. And the quantity divided by hk is precisely the one for which we got an expression using the mean value theorem twice. Okay, so I'll write that down, but you should do this for yourself. And we will do a bunch of examples showing that the conditions that we have put in our various theorems are really necessary. So, for example, it is possible that a function has both partial derivatives and, in fact, all directional derivatives, but still the function is, but still the total derivative does not exist, etc. Or what can happen is that all partial derivatives exist, the total derivatives exists, but the function is not continuous. Sorry, that came out completely wrong. What I mean is, the total derivative exists and therefore the partial derivatives also exist, but the function is not C1. That is, the derivative is not continuous. And therefore, necessarily what must happen? If f prime exists, then all the partial derivatives of f must exist. But f is not C1, so f prime is not continuous. So what can you say about the partial derivatives?
Like at least one of them has
At least one of them has to be discontinuous, no,
Yeah.
in view of the result that we proved. Because if all of them are continuous, then we know that that f prime is also continuous. So there are various examples to see what happens. And somehow the thing is, what happens is that the continuity in a multivariable situation is a very strong condition. What it is saying is that no matter what direction you come in, things are good. And not only that, the given any epsilon, there exists a delta. And then this delta, if you are within this distance delta, you could be within any direction. The same delta has to work in multiple directions. That is somehow a key. Anyway, so there are many standard examples. I have given you some examples in Rudin's exercises. Pramath has a bunch of examples in his notes, and I will go through, I think certainly those examples, maybe some more examples. I have given you an extra example in the homework. So you can also try to work out on your own. But next week, I'm not going to do anything new as such. Just if you have questions, then we will discuss questions in class. But otherwise, we'll just discuss a bunch of examples. So Monday, we will have the quiz. I'll also do Taylor's theorem. Hopefully, enough time will be left for that. And then in the remaining classes, we will do examples. Then we will have the second quiz on the following Monday. And immediately we will start the midterms exams. But then along with that, I will start new stuff, which is maxima and minima. Okay. Any other questions or any comments, questions, anything? All right, so
Sir,
yes, go ahead.
so can you again explain why did f double dash a h we took that as that expression? How we came up to that
Sorry.
for in the Taylor's theorem?
Are you talking about one variable case or multivariable case?
Multivariable.
Multivariable case. Okay. So do you mean, okay, so let me just make sure I understand the question. Are you talking about this?
Yes, sir.
Okay. So this is only heuristics, okay? But let us say I'm trying to find second order corrections. So is the first order term okay? Is this okay?
Yes, sir.
Yeah. So okay. So because see from A, I have step h1 in in x1 direction, h2 in x2 directions, and so on and so forth, right? So for each one of these, I have to calculate the first order correction, and that will just be whatever is the directional derivative times the distance that I have gone. This is exactly like sort of the physicsy analogy, if you will, right? Okay. So now I'm trying to calculate the second order corrections. So heuristically, what I'm thinking of is the following. Second order correction is going to be like second derivative. So second derivative is going to be of del by del xg of f. Right? So this is what I have over here. Right? So 1 second. This part. All right. Now all I'm trying to say is that I don't have very good answer over here. Okay. But what I'm saying is that since I applied both the operations, del by del xi and del by del xj. Somehow I have to take into account here how much I'm stepping in ith direction as well as jth direction. And to account for that, I'm multiplying by hi as well as hg. But it's not really a very good analogy, because then why am I dividing by 2 factorial? I think the better way to think of this is to really say that I am trying to match the second order partial derivatives, all of them. So does anyone have anything better to contribute? I mean, I'm just trying to do really pattern matching over here. So in one variable case, what did I do? I took the double derivative and I multiplied by h square and I divided by 2 factorial. So here the double derivative has many components in various directions. So all I'm saying is that when I take the component of the double derivative in the I and j direction, then the analog of multiplying by h square should be multiplying by h in the ith direction and h in the jth direction. So it's really pattern matching. But please do this calculation, which is to say that think of the expression that I've given over here in the theorem, right? So think of this whole thing, or rather the right hand side, just the right hand side of it, as a polynomial in variables h. Okay, now calculate the derivative of this. Calculate the various derivatives of this, various partial derivatives of this at the point of interest when h is equal to 0, that is. And then see, match the partial derivatives, the requisite partial derivatives of f at a. So that is one way to understand this. That I want to put in a multivariable polynomial and the desired, and I'm trying to match the features of f with features of this polynomial. The features that I'm matching are I'm trying to match as many partial derivatives as I can. So since this is in CM class, I match partial derivatives up to that point. Okay, anything else? All right, so let's stop for today and then we will continue on Monday.
Thank you, sir.
Thank you, sir.